Okay, so you want to buy a nuclear power plant, find a site, build the reactor, sell electricity to millions of people for 60 years straight. Sounds like the perfect business. Here is the strange part. A nuclear power plant is the only asset on Earth that can generate revenue every single minute for 6 decades without burning a single gram of fossil fuel. And it is also the asset class where governments with unlimited budgets, armies of engineers, and decades of planning have produced the most spectacular financial disasters in the history of human construction. How is that possible? We are going to find out. If you are new here, channel breaks down the real economics behind the industries and assets that power the world. Subscribe, new video every week. Now let's get into it. Here is the number that changes everything. In April 2024, Georgia Power completed Plant Vogtle, the first new nuclear reactors built in the United States in over 30 years. The original budget was $14 billion. The final cost was $35 billion. It finished 7 years late. Most expensive power plant ever built on Earth, and before it generated a single watt of electricity, the average Georgia household had already been charged $1,000 in pre-construction financing fees on their monthly power bills. Here is the part that should genuinely stop you. That is considered the success story. The identical reactor design being built simultaneously in South Carolina was abandoned halfway through construction. Federal prosecutors filed criminal charges against utility executives for concealing the cost overruns from regulators and investors. The half-built plant was demolished, $4 billion buried in the ground, nothing to show for it, except a cautionary tale that every person who has ever considered building a nuclear plant should be required to read before they sign anything. But here is what nobody tells you. The economics of nuclear power have two completely separate stories. Story of building one, and the story of owning one that already exists. And those two stories have almost nothing to do with each other. That gap between building and owning is the most important thing in this entire video. Nuclear power plants come in 3 configurations, and they are 3 completely different bets. The first is small modular reactors. Companies like NuScale have been developing reactors designed to cost between $1 and $3 billion and deploy in years rather than decades. They do not yet exist at commercial scale. They are the most talked about technology in energy and the least proven. The second is standard large reactors in countries that still have the industrial capability to build them. South Korea, China, the United Arab Emirates. A reactor in those markets costs between $10 and $20 billion. Expensive, but manageable. The third is building in the United States or Western Europe, and this is where the numbers become genuinely uncomfortable. Same reactor technology that costs $12 billion to build in South Korea costs $35 billion in Georgia. Not because the American version is better. Because the United States spent 40 years building almost no nuclear plants, and the entire industrial supply chain, the specialized welders, the quality assurance systems, the manufacturing base for reactor components atrophied. You cannot rebuild that supply chain in the time it takes to build one plant. So the first plant absorbs the cost of rebuilding everything. Hinkley Point C in the United Kingdom started construction in 2017 with an estimated cost of £18 billion. As of 2026, that estimate has nearly doubled to £48 billion, with the first reactor not expected until 2030. 13 years of construction, £48 billion, for 2 reactors that will run for 60 years if everything goes well. But all of that, the costs, the delays, construction disasters, is the wrong frame for understanding whether nuclear is a good investment. Because there is a number that almost nobody quotes when they'll talk about nuclear economics, and that number is what we are getting to next. Now, here is where the story completely inverts, and this is the part that the public conversation about nuclear almost always misses. Once a nuclear plant exists and is paid for, the economics flip entirely. A 1,000 megawatt reactor running at 90% capacity generates approximately 7.9 terawatt hours of electricity per year. At current wholesale electricity prices in the United States, that is annual revenue of between $275 million and $400 million. The operating cost, fuel, staff, maintenance, regulatory compliance runs between $40 and $60 per megawatt hour. Net of operating costs, a fully paid-for nuclear plant generates between 150 and $250 million in free cash flow every year for 60 years. Fuel cost barely moves because uranium represents a small fraction of total expenses. Unlike a gas plant where the fuel is the cost and the fuel price swings with global markets every quarter. A nuclear plant that is already built and already paid for is one of the most predictable cash flow machines in the energy industry. The problem is getting to that point without running out of money on the way. Revenue model has three components. Miss any one of them and your financial model is wrong. Three revenue streams running simultaneously on a single asset. If the math is this clean, why is the industry in trouble at all? Here's why. First is baseload electricity sales. Nuclear plants do not ramp up and down with demand. They run continuously at full power, 24 hours a day, 365 days a year, interrupted only by refueling outages that average 34 days every 18 months. That consistency is worth a premium in every electricity market on Earth. Grid operators pay specifically for reliable baseload capacity. Nuclear is not competing on price against solar. It is selling certainty. In electricity markets, certainty has a dollar value that intermittent sources structurally cannot capture. The second component is capacity payments and government support. 2024, the United States introduced a production tax credit of up to 1.5 cents per kilowatt hour for existing nuclear plants, a provision preserved by legislation in 2025. On a plant generating 8 terawatt hours annually, credit alone is worth $120 million per year. The government is paying nuclear plant owners to keep running. That is not a market signal. That is a policy decision. And it makes existing nuclear assets significantly more valuable than their pure electricity economics suggest. The third component is the decommissioning fund. Every nuclear plant owner is legally required to set aside money throughout the plant's life to cover eventual decommissioning, safely dismantling the reactor and managing radioactive waste. Cost runs between $500 million and $1 billion per plant, but the fund is invested and grows over decades. At many plants, the decommissioning fund has grown beyond the projected decommissioning cost, creating a financial asset the owner essentially inherits. Some of the most attractive nuclear acquisitions in recent history have been plants where the buyer paid a distressed price for the operating plant and received a decommissioning fund that more than covered the purchase price. Waste liability became the hidden profit. Now for the part the nuclear industry never leads with. Why, with all of this financial logic, do nuclear projects keep failing? Two patterns, always the same two. Mistake one, the construction trap. Nuclear plants do not fail because the technology does not work. They fail because construction consumes capital at a rate that becomes unsurvivable when timelines extend. Plant Vaatel was approved at $14 billion. By the time the first concrete was poured, it was already running behind schedule. Every month of delay on a $35 billion project carries financing costs in the hundreds of millions. The original contractor Westinghouse went bankrupt in 2017 mid-construction, unable to absorb the losses. It paid $3.7 billion to walk away. The owners then had to finish the plant themselves without the company that designed the reactor to guide them. 7 years late, 2.5 times the original budget. The construction trap is not a nuclear-specific failure. It is a mega-project failure. But in nuclear, stopping halfway is not an option. You cannot abandon a partially built reactor. You either finish it or you demolish it. South Carolina chose demolition, Georgia chose to finish. Both choices cost billions. Mistake two, merchant market mismatch. Nuclear plants are built to operate for 60 years. Electricity markets reprice every hour. That tension between a 60-year asset and an hourly commodity has destroyed more nuclear economics than any engineering failure ever has. When natural gas prices collapsed after the American shale revolution, wholesale electricity prices fell below the operating cost of nuclear plants across the entire merchant market. Bloomberg estimated that more than half of America's nuclear reactors were losing money, bleeding approximately $2.9 billion per year across the sector combined. Not because the plants were broken, because the electricity they were selling was worth less than it cost to produce it, and they had no way to reduce output or switch fuels to respond. A gas plant can shut down when prices drop. A nuclear plant cannot. It runs or it closes permanently. Here is the thing that the data shows, but the energy industry rarely states directly. Every country that has maintained successful nuclear economics over the long term has one thing in common. It is not superior engineering, it is not better safety culture, it is vertical integration. In France, EDF owns the reactors, owns the grid, and sells electricity to customers under regulated tariffs. In South Korea, KEPCO owns the entire chain from enrichment to retail billing. The merchant model, where an independent plant sells into a competitive market at a price it cannot control, is structurally incompatible with an asset whose economics only make sense across 60 years. The plant needs price stability. Market does not offer it. Every country that tried merchant nuclear eventually had to intervene with government support to keep the plants running. The economics always lead to the same conclusion. Nuclear power is a public utility pretending to be a market commodity. When it forgets which one it is, people lose money. Two scenarios, real numbers. Scenario 1, an existing plant acquired in the secondary market. Several US plants have sold below book value in recent years as owners tried to exit the merchant business. A buyer with a long time horizon acquires one at a distressed price. Annual revenue $250 to $350 million. Operating costs 100 to 150 million. Annual free cash flow 100 to 200 million dollars per year. With an inherited decommissioning fund already substantially built up, the acquisition economics can be extraordinary. Scenario 2, building new in the United States. 30 to 40 billion dollars over 10 to 15 years before the first dollar of revenue. Annual revenue at maturity 300 to 400 million. Payback period at those numbers, somewhere between 75 and 100 years. You are not building an investment, you are building national infrastructure. The only entities that can rationally build new nuclear are governments, regulated utilities with captive ratepayers, or companies that have found a way to transfer the construction risk elsewhere. Everyone else is funding a project that will outlive the people who approved it. And here is the question the industry cannot answer yet. Merchant nuclear fails and regulated nuclear works. What happens when an AI company with unlimited capital decides it needs a dedicated nuclear plant just to power its data centers? Microsoft has already signed a deal to restart 3 Mile Island. Amazon has purchased a nuclear-powered data campus in Pennsylvania. The demand is arriving before the supply chain exists to meet it. What that means for plant economics over the next decade is genuinely unknown. But for owners of existing plants, the timing could not be better. There is one more dimension that most nuclear economics coverage completely ignores, and it is the dimension that will define the next 20 years of the industry. Uranium. Every nuclear plant requires enriched uranium fuel, and as of 2025, Russia's Rosatom controls approximately 35% of the world's enrichment capacity. The United States, the EU, Japan, and South Korea have spent the years since Russia's invasion of Ukraine trying to reduce that dependency. Enrichment capacity cannot be built quickly. It takes years and billions to establish. Every Western plant owner sourcing enriched uranium from a country that can weaponize that supply is carrying a geopolitical risk that does not appear on any standard financial model. The plant runs on physics. The fuel runs on politics. And the gap between those two realities has never been wider than it is right now. Whether small modular reactors deliver on their cost projections, whether the AI-driven electricity surge of the mid-2020s makes nuclear the only viable solution for data centers consuming gigawatts continuously, whether any Western government has the institutional patience to see a 20-year program through, none of that has an answer yet. What does have an answer is the 60-year-old plant sitting in a deregulated American market, generating $200 million a year in free cash flow, owned by a utility quietly trying to exit the business. That plant exists today. That economics works today. Everything else is still waiting for proof. The next video goes inside the economics of the business that builds the fuel for this one. Subscribe so you are there when it drops. The counter-argument you will hear from the energy transition camp is that solar and wind have fallen so far in cost that nuclear is simply no longer economically competitive, and any capital spent on new nuclear is capital wasted. That argument is partially correct and almost entirely misleading. Solar and wind are cheap to build and free to fuel. They are also intermittent. They produce power when the sun shines and the wind blows, which is not always when the grid needs it. Battery storage technology required to make intermittent sources function as reliable baseload does not yet exist at the scale or cost that would make them a structural substitute for a plant running at 92% capacity around the clock. The grid needs firm power. Nuclear is firm power. The debate is not about which technology is cheapest to build in isolation. It is about which combination produces a reliable grid at the lowest total system cost. That calculation, done honestly, always includes nuclear. The answer is just not the one either side of the debate wants to hear. So if you decide to buy a nuclear power plant, just remember the only rule that actually matters in this business. The atom does not care about your construction schedule, and neither does the interest clock.